I will share my screen first. Can you guys see my screen?
Yes.
Okay. So today I will talk about logistic regression. I will start with some examples and then try to go a little bit deeper into the math behind logistic regression. And then I'm going to talk about hypothesis function, decision boundary, and cost function. And I will leave that evaluation matrix for Munziel. Okay. So just to begin, um, can somebody tell me, when do you want to use linear regression instead of, let's say, logistic regression? So when do you want to use linear regression? Or what does linear regression do? So what is the output of linear regression? Anybody?
I think there is an answer in the chat.
Okay. Oh, sorry. I cannot see the chat. Okay, so I will go ahead and answer that question. So we're going to use linear regression when we need our output to be in a numerical value, all right, or continuous value. That's when we're going to use linear regression. And whenever our output is, let's say, class, or instead of numerical values, if we have class, if our label y's are class, then we want to use logistic regression. All right. I'm pretty sure most of you already know some examples of logistic regression. In one case where I use logistic regression is to predict when my student is going to pass or fail. So that's two class. And sometimes instead of just pass and fail, if I want to check whether my students will get A, B, C, D, or F, that's the time I want to use multi-class logistic regression. And another famous example is whether email is spam or not. So that's a classification problem as well. So, and another classification is whether your online transaction is fraudulent or not. And if you have taken Andrew Ng class, he's going to use this cancer problem, whether the cancer is benign or malignant, right? These are some examples of logistic regression. So instead of continuous numerical value, we have class, right? So I'm gonna get right into a little bit math of this logistic regression. So I'm gonna label, I will talk about two classes. So my Y values are whether a student will pass or fail, or whether the cancer will be benign or malignant. So yes or no, or false or positive or negative, true or false. So I'm gonna label them as Y is equal to 0 and 1. So I'm gonna convert them into numerical values, 0 and 1, okay? So so this is my x. I have a diagram right here. So I have the x values and y values. Okay. So for example, this is my y is equal to 0 right here. And this is my, let's say, y is equal to 1 right here. All my students that's going to pass, let's say they are in the upper y is equal to 1. And where my student fell, they are right here. Okay. So if I were to perform a linear regression on this data. So all I do is try to fit a line passing to right here. So I guess I can still use linear regression right here, try to fit a line, and then I can say, oh, okay, anytime my data is, let's say right here, let's say this is your X is your high school GPA right here. And based on the high school GPA, I'm trying to predict whether the student will pass or fail. And I will say anything that lies above this line will pass that class, and anything that lies above this line will fail that class. So I will use that as my threshold, which is 0.5. So what I'm saying is, if my Y value, so this line will predict some number, and if my Y value, this will predict your Y, and if that value is 0.5 or greater, I'm going to say that's a true class or a positive class. And if it is less than 0.5, I'm going to say, okay, predict me false class or negative class, right? So can somebody tell me what is wrong or what are the few things that can go wrong in this model? So I'm mainly interested in my Y values. So what do you think, what can go wrong with this prediction? What does this line predict?
I think the Y value is invalid.
The Y value,
because the valid values are 0 and 1, right?
Yep, that's a good answer. That's one of the answer. So still this line, if you use a linear regression, this Y will be some numerical values, and it's a continuous value, right? So, but what we are only interested in these two values, 0 and 1. And obviously, if you use regression, you cannot guarantee that you'll get some values where there are negative values, somewhere around these values and somewhere very high values, all right? That's one of the problem with this model. And another problem is, let's say I add in data somewhere right here. Obviously, this is not an outlier, all right? This student just have a very high GPA, let's say 4.0, and I know that student is going to pass. But what happens with this is, if you try to run a linear regression on this one, maybe this will try to fit that data right there, and my new threshold will be right here. So this line will now anything that lies so anything below this, obviously that should be your classification right here, right? And with this addition of data, my line try to fit somewhere right here, and this seems like this should be the new a boundary right here, right, to predict whether my Y values is whether the student's going to pass or fail, right? That's another problem with this model. So instead of using this linear regression on this one, what we're going to do today is we're going to use this logistic regression, right? So and so my goal is to predict the Y values, and basically it should give me 0 and 1. All right, that's the output I want. And I know that my linear regression, if I try to use this, my values will be out of the boundary, all right, not the valid values. So what I'm going to do is first this question. Let's say I give you an X with let's say two different, so this is just one training example. Let's say you have 1, 2, and 3, all right, with two different features right here. And I give you theta is equal to, let's say, 4, 5, and 6. All right, and these are my thetas. So if I give you X and theta, can somebody tell me how, let's say you are performing linear regression, how do I find how do you predict your Y value? Let's call it Y hat. if I give you x and theta, and if you were to use linear regression, what is one thing you can do to find your y value? I'm using my hypothesis for linear function is what should be, if I want to use linear regression and you have your x and theta, how are you supposed to find your predict the y value? So, and you have two arrays right here. You have x and theta. That's what you need to find your hypothesis to predict the y value.
You mean with the linear function or?
Yeah, with the linear function. Okay, so which is, let's say, if I want to use linear regression, that's a linear function. So I said linear regression, theta 0 x0 plus theta 1 x1, theta 2 x2, and so on, right? So what I'm basically doing is I'm multiplying. You can think of this as a matrix multiplication or a dot product. So how would I predict my y value? I would multiply this 4 times 1, x0 times theta 0, 4, and then plus 10 plus 18, and this gives me 32, I think. That's how I predict my y value, right? In linear regression. But in logistic regression, what I would do is I'm still using this linear term, but I'm gonna, once I get my this value, y value, I'm gonna pass it to a different function, which is called g function. All right, and it stands for this logistic. This is called logistic function, and why I'm passing inside this function is so that I can have the output strictly between 0 and 1. So the graph of this logistic function or sigmoid function looks like this, and your y values are restricted from 0 to 1. Okay, and why I'm using this logistic function right here instead of other functions? Well, that actually that can be any study of a day or maybe a week for itself. All right. So, but we use this function, and what we do is we calculate this. We're still doing this theta transpose x. All right. We're still multiplying. We're still using that linear relation, and in order to have my values between 0 and 1, I'm gonna use the sigmoid function. All right, and that will restrict my values between 0 and 1, right? And how is this hypothesis function defined, or how you should think of this hypothesis function is think of this like flipping a coin toss. All right, so you only get either a head or tail. So somehow it has to do with the probability. All right, so what does this hypothesis function does is it estimates the probability that with the given input x, that's the probability to predict a y is equals to 1, whether the students will pass or fail. So this hypothesis function estimates the probability, right? Whether the student will pass or fail. And let me remind you, the probability is always between 0 and 1. Okay, and that's another reason we use the sigmoid function. And if I say that if my hypothesis function predicts, let's say 0.7, that's a 70% chance for that student that he or she will pass given that input features. Okay, and since this is a probability, another thing you can do is probability of y is equal to 1 given x parameterized by this theta plus probability of y is equal to 0 given x times theta should be equal to 1. right? So that comes from probability, and these are the only two events whether you will get hit and torn. So they should add up to 1. Okay. Any questions so far?
So like just before you showed like sigmoid function, so yeah, you were talking about like it takes time. So can you like summarize a little why you choose the sigmoid logistic function?
Oh, why I use sigmoid? That's something. Okay, so this is this has to depend. Like this is a I cannot explain right now, but this comes from something called maximum likelihood, and this is the reason we use this. All right. So instead of using the other function, it's they derive that this is the best function to use in this case. So and it has to depend on the probabilities. And
I think yes, that's the concept that we need to go and explore. But I think the simple thing to look at is because we are trying to classify a binary output, right? 0 and 1. So 0 and 1, right? So for that, sigmoid function can be used so that we can get this probability score between the two classes that we are trying to predict.
and thank you, Monjil. And another reason is this is mathematically done. We are not just using it randomly, and there is a lot of heavy math involved in it. And this function has been derived particularly for this logistic regression. Sorry, yeah, logistic regression case. Does that answer your question?
So I mean, so this like when we use this this logistic function, so every time you define this sigmoid function, is that the answer?
Yes, kind of. Correct me if I'm wrong, Manjal, but you need to have some like this function. If you use linear regression, you're gonna get 32, right? But what we need is we just need two values. We need our hypothesis function, or our prediction should be only 0 and 1. All right, and so somehow I need to convert this 32 to 0 and 1, some values between 0 and 1, and this function just does that. No matter what your input is, you can have 4, 5, 6, you can have 100, 200, and this is a way, one of the way to convert my y values to 0 and 1. So it limits your input strictly between 0 and 1.
So like for this, like every function we have, like for example, this case we have the range of from 0 to 1. So that's why we select this function. So means for this kind of logistic function, every time we have to define the maximum likelihood estimate or that kind of thing.
Well, you don't have to. You can use other functions too, but it might have to do later on when we talk about the cost function. You want to minimize the cost as well, right? And you want to be able to find that minimum point. And we want our loss function to behave like this graph or something like this graph. So where you can actually find your minimum using gradient descent. And that's one of the reasons we use this.
Yeah, okay. Yeah, I know as this function has only select the answer between 0 and 1. It's like, okay.
That's the most only answer I have for right now. Just because it's between 0 and 1, we use that. But can you use some other function? Yes, you can. And also when you use those functions later, when we derive the cost, you have to see whether it's going to be those convex functions or not.
I think so you know about the tanh function, right, Sushilji?
Yeah.
Tanh functions will have the values from -1 to 1, right?
That's
So in sigmoid functions, the value is between 0 to 1. So whenever we are building a classification model, even though we are trying to predict a class, but we are trying to estimate the probability score. So the probability score is from 0 to 1, right? So we need to get the values between 0 to 1. And depending upon the threshold that we set, so for example, if we are setting threshold at 0.5, so any value from 0.5 will be the positive class. That means, let's say for instance here, if you are trying to predict the grade of a student, so if you are saying given these features, the grade is A, right? So when you pass the feature in this logistic regression, and if the probability score is 0.67, then it is A, right? Because it is greater than threshold setting. So our goal here is to estimate the probability score. So that's why sigmoid function, since it has value range from 0 to 1, we use the sigmoid function.
So yeah, for the case, this is for only the binomial feature. Yes?
Yes, when the target variable is binary.
Okay, I
But
understand.
let's say
Yep.
if your target variable is multi-class, right? Then we have another function called softmax.
Okay, yeah, now I understand that, like when every time we go with the type of example, then we come to the point that there should be some function that define that particular class. Yes.
Oh, exactly. Yeah, there are
Right,
different
right.
functions that we can use. This is pretty much the example for sigmoid functions when we're using the binary class.
Okay, so the logic is like the maximum likelihood things. Okay, thank you.
Right. So we talked about this probability being both of the probability added to 1. So now I want to quickly talk about the decision boundaries, and it has to do with the threshold we set up. All right. So like Manjil said just right now, so our sigmoid function looks like this, strictly between 0 and 1, and there is some threshold we set, right? So what we are saying is every time my y values, all right? So again, it's predicting the y hat with this theta transpose x. So that is matrix multiplication between thetas and x. So it's going to predict y, and then we're going to send this inside the sigmoid function, and it's going to give me some values, all right, between 0 and 1. And I'm going to set a threshold, and I'm going to say, let's say if it is greater, if that y value it produced is greater than or equal to 0.5, so that's a true class. And if it is less than 0.5, then it's just false or fail. Okay. And now I want to show you one example right here. So I have my x theta, x1, x2, and I have my theta. So what I should do first is I should multiply x and thetas, all right? So I'm going to multiply x naught times 6. So first with first, and x1 times 3. So this is, let's say I already have the theta, assuming I already found my theta, and then I have 0 times x2. And what I'm going to do is I'm going to send it inside the g function, right? So which is negative 6 x naught plus 3 x1, and this last term goes to 0. Okay. So and if you look at this, graph, let me go back to graph right here. There's this few things. I'm about to show you the relation between x and y right here. So I said, so if this is the function, which is s theta of x, is you're going to send that to theta transpose x, and that's your y. All right, that's in this line, right? And every time it predicts your y greater than, that's the positive class right here. And every time it predicts some values that is less than 0 point, and it's a negative class right here. But if you look at it, if you think of this as a function right here, so like these are the g values, and so that's your g axis, right? And that's your y values, right? This is like an x-axis, that's your y-axis. And it says, so every time, so there is right, this every time g is greater than 0, all right? Whenever your x, you can think of this, whenever your x is greater than 0, all your y values are greater than 0.5. And every time my X value is less than 0, my Y values are less than 0. Okay. Sorry, my Y values are less than 0.5. Okay. Okay. So I have this theta transpose X, and what I did is I send it to the sigmoid function. All right, I'm sending the sigmoid function, and I will write my condition. All right, is greater than or equal to 0.5 every time whenever my G or my X value is greater than 0. All right, so if you rewrite this one, that's a G function. So that means your decision boundary will be 6x plus 3x1 is greater than or equal to 0. So add 6x0 on both sides. Okay. And usually we take x0 as, sorry, I forgot to mention that. And where is that example? And it should, we usually take that as in 1. Okay. So I will substitute that values. 6 times 1, divide both sides by 3. So I will get 2. Okay. So now what I mean by decision boundary is, let me, so this is your, let's say, oh, what I did. So that should be my x1, that should be my x1. Okay. You have an x1 right here. Let's say you have an x2 right here. What it says is every time my x1 is greater than 2, so this is 1, 2, and that should be the boundary, right? Every time my x1 is greater than 2, so that means my boundary should be right here. So that's my positive or true. I will call this pass, and that's the false region. Any question what I just did? So your true data should lie on this one, right? So that's the, let's say if you plot it, or maybe somewhere right here. So that's the false region, and that's the true region. That's all I'm saying when you plot this x1 and x2 features.
So you select this matrix, like column matrix for these theta values, like.
Oh
and
yeah, that's well, that's just my bad notation. Is that you, Suresh?
I'm Sushil.
Oh, Susil, sorry. Yeah, that's my bad notation. So you can, if you want, you can write this as -2, 1, 1.
No, I'm saying like, so the way you pick these metrics, how we can connect with our binary classification decision things.
Oh, how, let's say we're gonna use gradient descent to find these thetas. For right now, I will just give you an example. Let's say we already have these thetas. Where should be the boundaries?
For example, in your case, like x1 greater than 2, like, so how do you connect this with your data sets? Like, or this, it's just like a math we are doing now.
Oh, how do I connect? Let's say if you, let's say, so for example, in this one, let's say if I have my GPA, I'm only considering about GPA, and I have like some high GPA right here, maybe, and they're supposed to be the one right here. And if they have low score GPA, this, and that's the boundary I'm trying to find. This one using that thetas.
Okay.
All right. And similarly, sometimes, yeah.
So Bimal brother. So sorry. So boundary is just like we are trying to separate our 0 and 1, right? Like if you're trying to predict, let's say, cancer or non-cancer. So boundary is the point where it is giving us that threshold that our model or classifier is able to classify cancer and non-cancer class, right?
Like, for example, you provide me like initially the example of grade, like 67%, more than 60%. will be A grade. So
Right.
now we have defining the column matrix. Then how can we select these matrix, like, or like I'm missing something? Because we are talking about like the binary classification, right?
Yeah, we're talking about binary classification.
So the way, yeah, like we have the different matrix here, like sometimes we have this. So I think
So I think, let's say this is your GPA, and this is your, let's say, what is that, semester hours, how many classes you are taking. So let's say that's the number of classes, right? And if you have this information and you plot this, think of this like you plot this on your axis. So so your data points should be, let's say you have x1 and x2. If you plot this, and you will get some kind of graph, right? So maybe not exactly like this, maybe some data is right here. So let me draw something like that, maybe something right here, maybe something right here. And all I'm saying is like there's a way to find the boundaries that separates this, like let's use the triangle and x, maybe x right there, maybe some x right there, or maybe some triangle right there. So it seems like this should be the boundary, and this with the help of thetas, we can find that boundaries using the input features. So this boundary actually is totally dependent on the thetas you pick.
So we need to estimate our theta such that, you know, the separability is very good, right?
Exactly.
Yeah.
And I'm just giving you the thetas randomly. That's going to make it work here for nice example. That's why I have this theta. But to find this theta is a whole different text, and that's our actually the main goal, to minimize minimize the cost function and find these thetas that will actually do the job.
Yes. Now this brings another interview question. What do you mean by parametric and non-parametric models? You know, the linear regression and logistic regressions, they are parametric models, because all we are doing is we're estimating the parameters here. So next week onwards, we are also going to see about the non-parametric models like decision trees, random forest, XGBoost, etc. But this is a very important concept. Thank you so much, Bimal sir, for teaching us.
No problem. And so if I were to, I'm going to go quickly over this second example I have, and this might make a little bit more sense, or this might make it worse. All right. So let's give it a try. And again, I have the same data points. I have my x1 and x2. All right. And again, that should be 1. And if I use this theta and this x, so I'm supposed to get -2 plus x1 plus x2 should be greater than or equal to 0. All right. So what I did is I did theta transpose x, and I send it to sigmoid function. And every time it should be greater than 0. That's going to happen only when this whole thing is greater than or equal to 0. Okay. And this is nothing, but this is the equation of line. I'm going to call it x2 should be greater than maybe negative x plus 2. And this is nothing but the equation of line. All right. So let's say if you were to, so negative slope with positive 2. So maybe that should be your decision boundary, right? And maybe data will write right here and right here. And that's how we're going to find the boundaries. And it's so easy to show in like 2 variables. It might get, I don't think I can do that in higher dimensions. Okay? And that's all for the boundaries. Now, I don't have much to talk about the cost function and the gradient descent algorithm. All I can say here is, if you guys remember, we did the mean square error. All right, this term is very important, and that's the error we use for mean square error, right? So what we did is we predict y hat, and we found the residual or the error, and then we squared it, and then we sum over all these things, and we divide it by 1 over for just for the scaling. Okay. And And can we do the same thing in logistic regression? And one thing we cannot do this is your y hat actually come from sigmoid function. Remember, this is g of g, and this is not a linear function. Okay, and since this is not a linear function, what it does is whenever you run this gradient descent algorithm, you are not guaranteed to have a local minimum or global minimum, right? So it's going to have, it may have too many minimum points, and you don't know, you are not guaranteed whether you will get the required one or not. All right. So in order to make, that's called convex function, all right, like I mentioned it before. So our goal is to find a function that does something like this, or that does something like this, right? These are convex function. In order to make this, in order to make sure that whenever we perform the minimization, we get that minimum, we use something called log, negative of log, all right? So if you guys remember log function is the opposite of exponential function, all right? Your exponential function looks like this, and that's your e to the power 0, which is 1 right here. And this is, your log function is exactly opposite of the linear function, or you can call it inverse function. So it's a reflection on y is equals to x, and your log functions looks like this, right? That's your log function. And log function is you have an asymptote right here. It's not going to touch that. You cannot plug y is equals to 0, this line, and it's strictly defined in the positive x-axis only, right? And what does the negative log does is, let me draw this again. And I just want to quickly point it out why this works. And so my log function is actually like this. So, and whenever I draw a negative of x, that's a reflection on x-axis. So this graph's supposed to behave like this, right? And all I'm interested is in this part, 0 to 1 part. So, and that should be your error or cost. Anybody remember the difference between the loss and the cost? And it doesn't touch right here. Tries to get 0, right? Actually, it does. Sorry. Okay, so the difference, I think Manzil, correct me if I'm wrong. The cost is for a one particular training example, and when you sum all that cost, it is the loss function. Okay, and why this negative of log y works is, let's say this is your 2 positive, and this is your 1. So if you predict that your you'll get 2 positive, you'll get a 2 positive, your error will go to 0, but you are supposed to predict 1. And if you try to predict your y value to 0, so let's say if you try to go somewhere around here, and you should be penalized heavily. And that's the reason that I mean, you can kind of see that this works. All right, so every time I make a 2 prediction, my cost is 0, and every time I make a wrong prediction, I'm penalized heavily, right? And similarly, another version is for the false is this one, and just because it's a binary, you can combine them into one simplified form. Okay, and this is exactly same thing as this one. Okay, and so for example, if your y hat is 1, this becomes 1 minus 1, this part goes to 0, so you'll simply get this when y is equal to 1. Let's say when y is equal to 0, and when y is equal to 0, so this part will cancel, and you'll simply get the second one. So this is just a simplified version of the same cost function. And another nice thing about using this sigmoid function and this log cost function is the gradient descent algorithm. All right. And this should look very familiar to you guys. And this is nothing but the same gradient descent for linear regression. And it took me a whole day to derive this. Actually, if you remember, in gradient descent is the minimization problem, and what we did is we let's say our graph was something like this, and let's say we started we initialize as that theta. We find the slope at that point, and what we did is we use the learning rate, so that's the theta we started. Let's call it theta 0. And what we did is we find the slope, all right? And slope has to do with the derivative. So, and that's my learning rate. And once I update this, okay, and then I will get my new theta. That's what I did, right? So I got this point, I'm gonna draw a transient line again, and so on, all right? And it's not so clear that whether you use this, the cost function we defined for linear regression was something like 1/2m, which is y hat minus y whole square. And if you take the derivative of this guy, still you get this guy, and you take the derivative of this crazy thing, and you still get this one, which simply says take the difference of your y's, predicted y, and in your real y, and multiply it with the corresponding x. And we I think we went over that in detail last class too. So that's the same gradient descent we talked last time. Any questions, guys?
So this theta j on the right hand side is the one step less than the actual theta j. Am I right? Like
Yes.
okay.
So you talking about this one and this one, right?
Yes.
Okay, yeah. So one step less. And well, I forgot what I was about to say. And nice thing about it is if you import some function from Python, you don't need to know none of this. So even if this is too much, you can simply import your some modules in Python, and they will run this. But it's good to have just a high level understanding of what was going in logistic regression. And that's all I have. I want to give my time to Manjil and Damodar. So Manjil going to talk about the evaluation matrix. And
Can I?
thank you.
Yeah. Can you bring your slide down?
Yeah.
No, up probably.
You mean right here, or?
Yeah, I think we can use the slide so that
Okay.
go up once, up. Here, I just wanna go up. Yeah, I just want to, yes, in this slide, I just want to say that it's not only about building a model or building a classifier. So it's all about how good we can build it so that it can predict well, right? So we do all this to optimize our parameters better, so that it is able to predict accurately. So now we're talking about classification problem. Now what are prediction? We talked about probability score, we talked about different class. Now let's dive deeper and see how we are going to evaluate our model, right? So can you go slide down? Yeah, on the confusion matrix. Yes. So here, this is the confusion matrix. So remember, we have the binary class, right? So y is nothing but our target variable, and there is two class, 0 and 1, which is binary, right? So 0. So let's take a use case. So use case would be whether or not a patient would have a cancer or not, or patient would have heart disease or not, which data set will be looking after 20 minutes or so, right? So 0 means patient does not have heart disease. 1 means patient has a heart disease. So 1, we call it as a true positive. So if you see here in the blue box, it's called a true positive. So when patient has a heart disease, that's what we're trying to predict. It's a positive class or our true positive, right? When it is 0, that means it's a negative class, right? Which is true negative here, or the negative class. So 1 we call it as a positive class, 0 we call it as a negative class. So the important thing to understand and remember is the class that we are trying to predict, we always call it as a positive class. Okay, the class that we're trying to predict is always a positive class. So I have a question. Let's say I want to build a classifier. I want to build a classifier or a model that will predict whether or not a transaction would be fraud. So what would be my positive class here? Can anyone? So if I want to build a model or a classifier that would predict whether or not a transaction would be a fraud or not, fraudulent or not, what would be my what is my positive class here in this example?
I think it's fraudulent itself.
Yes, right. The fraudulent transaction is my positive class. Non-fraudulent is my negative class. So think about this, right? So our goal is to build a classifier that can predict accurately positive class as a positive class and negative class as a negative class, right? So that means we are trying to build a classifier so that it can accurately predict its respective classes, right? But I have a question. Do you think in a real scenario that is possible? Do you think it is possible that we are going to get like uh, are we able to build a classifier like that can classify positive class as a positive class and negative class as a negative class? Any answer?
Maybe not.
Maybe not, right? Maybe not. So what will happen is there is a chance that a sample gets misclassified. That a sample gets misclassified, right? Understand, this is a very important concept. And if you are trying to switch your career to data science, you know, interview question, 130% this question they'll ask about classification metrics. So, there is a chance that it is going to be misclassified. 100% the samples is going to misclassify. So what do we mean by misclassification? Okay, so misclassification is, if you see here, this is we call as a confusion matrix. Okay, confusion matrix, this side there is a true response. What is our true, right? Y equals to 1 is fraudulent, y equals to 0 is non-fraudulent, and this is predicted, what we predicted, right? Predicted that it's a fraudulent, it's non-fraudulent. Now think about this. When we are accurately predicting the positive class as a positive class, it's a true positive. Okay, when we are predicting, our true response is 1 or fraudulent and our predicted response is 1, we called it as a true positive. And when our true response is non-fraudulent and we predict it as a non-fraudulent, then it's called a true negative. Okay, no question in true positive and true negative. Now there is a misclassification. Let's say our transaction was fraudulent, but it didn't predict as fraudulent. So what is that, right? Our target was, our response was fraudulent, but our predicted was non-fraudulent. It is called false negative. Okay, it is called false negative. Now when our target was non-fraudulent and when it predicted a fraudulent, it's called false positive, right? So our misclassification samples are either false negative or false positive, right? So that means, so now think about this. Our goal is to predict a classifier which can accurately predict two classes: positive class as a positive class, negative class as a negative class. But in real case, in a real world scenario, that is never the case. There is always misclassification. So based on what misclassifications are, we said if response is 1 but it is predicting 0, it is false negative. It response is 0, if it is predicted 1, then it is called a false positive. So, depending on your previous experience, is anyone have any experience in dealing with false negative and false positive before in any areas? Anyone has any experience? Okay, no. So false negative and false positives are dangerous, um, you know, depending upon what use case you are trying to solve. Let me give you an example, right? False negative is what I said was if your true response is 1 or fraudulent and it didn't predicted as fraudulent, then it's a false negative. Okay, think about this. In a real world scenario, you're trying to build a model, given the features, whether or not a person would have a cancer or not. Think about this. If the true response or the true target was cancer, but when it predicted, it didn't predicted a cancer, right? That's a false negative, right? In this scenario, this this misclassification is very dangerous, right? In this use case, right? False negative is very dangerous, right? You don't want a patient to be cancer and not predicted to be a cancer, right? Very dangerous. So in this scenario, false negative is always dangerous. Now there can be scenario where false positive is dangerous. So for example, let's say you're trying to build a classifier which are able to predict spam or non-spam emails, right? So let's say your email was classified as spam. A manager sent you an email and that email was classified as a spam email and went into your spam inbox and kept there, right? But it was not, right? So this is an example of false positive. When what happened, you were not able to respond to your manager, right? In this case, the false positive is dangerous. So depending upon the use cases, we need to take care of our false negative and false positive, right? So if you see in the confusion matrix, we are true positive, false negative, false positive, and true negative. So using this component, we derive different evaluation metrics called accuracy, precision, recall, F1 score, etc. So anybody has any question till now here?
So the confusion is happening because of the, I mean, the logistic function we select, or like it's already the systematic error we have.
No. So, okay. So we build the model, right? Now we predict it. Okay. We will see it after a while when we do a coding. But think about this. We build a model, right? Once we build the model, we'll predict our result, right? We will have the data set of prediction, right? So once we have the data set, we will put these predicted values in this confusion matrix. Okay, how many of them we predict, how many of them in the data set where true response was y and we predicted y equals to 1? How many of them was y equals to 0 and we predicted y equals to 0? And how many of them misclassified? So we put in this matrix. So let's say, for example, we have 100 data set where we are predicting, right? So out of that 100 data set, 30 data point we predicted it right, y equals to 1. So in this true positive we update 30, right? In true negative we update 30. Okay, in false positive we update 20, and in predicted we update 20, right? So 30, 30, 20, 20. Now using this we derive something called accuracy, precision, and recall. Make sense, Sushilji?
Yeah.
Okay. Any other question? Okay. So Bimal sir, can you stop sharing? I need to say.
Okay. Oh, sorry.
No, no, you're fine. Yeah, I just need to say. Okay, let me share my screen. And okay, let me go to the performance metrics. Why I want to walk you through this is two things. I want to show you Medium or towards data science is a very, very good resource if you are learning data science. A lot of creators, content creators have made a very good post on different concepts of data science. I am a subscriber. I pay monthly subscription to it. It's like $4 or $5. You can also subscribe it. It'll give you like thousands thousands of contents. Um, so I have so here I have put all the links for the Medium and towards data science. So it's already there in the Google Drive. If you can go and see on week 9, you can see there are different contents here. You can always go and see and check. So here I talked about confusion metrics, which we talked about it, right? So if you go and see it, it'll clearly explain what true positive is, what true negative is, what false positive is, what false negative is, right? And then I also talked about, when false negative is dangerous, when you need to minimize it, and where false positive is dangerous, where you need to minimize it, right? You can always go back and check. So now think about this, right? As I have mentioned, let's say this is your uh, this is your this is your confusion matrix. Let's put a number, right? Let's say out of 100 samples your true positive were 40, right? And your true negative were 30, right? Your false negative were 10 and false positive were 20, right? Now you have a numbers here, right? So now what you can do is now you can calculate the accuracy of your model. Okay, hey, how accurate was our model in predicting a different class, right? So there is a formula here. Accuracy, what your accuracy is, it's your true positive plus your true negative, because this is your actuals, right? True positive plus true negative divided by overall samples, right? Which will give you the accuracy score. And this score is always between 0 to 1. Okay. So let's say your accuracy is, right, as I said, your true positive out of that 100 samples, your true positive has 40, your true negative has 30, right? 70 plus 30 divided by 100. How much? 0.7. That means it is 70%. Your accuracy of your model is 70%. 70% of the time, your model is predicting accuracy. Positive class is a positive class and negative class is a negative class. So that's your accuracy score, right? So now see here, denominator, right? In accuracy, your denominator is everything, your overall prediction, right? Overall samples. And your numerator is TP plus and TN, which is your true positive plus true negative. Now I'll talk about it, but let's go to there is another concept when to use accuracy. I'll talk about it, but before that I need to talk about class imbalance. So I'll talk about that and I'll come back here. But next thing is precision. So I talked about false positive, right? The example of email classifier. Think about this. You are building a classifier that classifies whether or not your email is spam or non-spam, right? Your manager sends you an email. Your email is classified as email, spam, goes to the spam inbox. You missed it, right? You missed it. It's a problem, right? So which is a false positive. The email was not spam, but it was predicted as spam. So now you need to take care of your false positive, right? So you need to understand what your precision is, right? So in precision, it's all about you're checking your true positive. Okay, you're taking your true positive, and then you're taking with your true positive and for your false positive, right? So you are basically calculating how accurately your model is classifying your positive class as a positive class, right? So so what you're doing here is you're taking your true positive and dividing by true positive plus your false positive. So it will give you the values from 0 to 1, which is basically you're saying, okay, you are saying you have 96% of your precision. You're saying 4% of your values are misclassified as a false positive, right? So false positive, you're always dividing it by your true positive plus your false positive. Now there is another example, recall, right? Recall is all about false negative, right? When you do not want your positive class to be classified as a negative class, right? You do not want samples which was a cancer as a non-cancer patient, right? You don't want that. So it's all about predicting your positive class accurately as a proper positive class, right? So that's where recall comes into play. And here it's all about taking your true positive, dividing it by your true positive plus your false negative, which will give you a recall value, right? So now, when to use your precision and when to use the recall? I always gave you an example. There is no hard and fast rule. You need to use recall, and here you need to use a precision here, right? It only depends on use case, what your use case is. If your use case is more sensitive towards false negative, you definitely wants to minimize your false negative. If your use case is more towards false positives, you want to minimize your false positive. Okay. I would highly encourage every one of you to go and go through this article. This is a very nice article to give a read. It gives lot of understanding on evaluation metrics with some business use cases. So any problem here before I come into this part? Any question here? Okay, no question. Okay, now I have a question for every one of you. Okay, so since we are saying we are trying to build a model, a classifier, right? Let's take an example, right? Last week we saw how Damodar Bhai helped us to understand about a machine learning pipeline. He gave us an example about my banking example, where he said, hey, if we are trying to build a machine learning model which will be able to classify fraudulent and non-fraudulent transaction. Now, I want to ask you, in the banking overall data set, which data sets is very less, fraudulent transaction or non-fraudulent transaction? Which has more transaction, fraudulent transaction or non-fraudulent transaction?
Non-fraudulent.
Non-fraudulent transaction, what, less or more?
Less.
Less, right? Non-fraudulent transaction is less. That means we have more non-fraudulent transaction, right? Right. So
Yeah,
let's,
yeah.
if a bank has million data sets, right? Million transactions. So out of that million transaction, how many percent do you think would be a a fraudulent transaction? Probably 2%, 3%, right? Probably 2%, 3%, not more than that, right? Probably 1%. That means there is a class imbalance, right? That means we have a non-fraudulent transaction more, we have a fraudulent transaction very less. We call that kind of scenario as a class imbalance scenario. And this is very dominant, especially when you're trying to build some sort of classification algorithm. Class imbalance problem is a very common. So there are different, so now whenever we are trying to check the accuracy of model, now think about this. Let's say you have 99% of your transaction as non-fraudulent and 1% as fraudulent. What will happen to accuracy?
99%.
Right? Automatically, right? It will automatically predict. So in this case, what we need to do? because we do not want our model to be biased, right? So what we need to do is, there are different techniques. We, first of all, definitely accuracy is not a good model metrics to evaluate in this case of scenario. We need to check recall and precision, right? Or F1 score. There are other metrics too. You can go through this documentation. So other strategy, what we can do is, we can do some class balance techniques, right? We can balance our uh, our fraudulent data set and non-fraudulent data set, train the model, do it. So there are, I have posted, you can go through these links. I have, so here, if you see here, there is a link for imbalanced data set classification. What you need, what you can do if your data set is is not balanced, and we'll see that when we are doing coding. But you can go and you can check it. So that's all I have regarding evaluation metrics for our classification model. uh, Now we'll be doing a coding. So I would like to ask you everyone, if, and check to see if you have downloaded this data set and this Jupyter notebook or not. So if you have downloaded, please give a thumbs up, because Damodar will help us to walk through the code and help us to build the classifier. Um, there is another part of evaluation metrics too, this understanding AUC ROC curve, which I'll go through next time. Since we'll be also dealing with other algorithms as well. At that time, I'll go every one of these evaluation metrics too. But for now, okay, for now, let's build a classifier, right? Let's build and see what we just learned, right? How about that? So with that, I would like to give it to Damodar.
Thank you, Monzil. Hey, how's everyone doing today?
Good, sir.
Okay, so I want to show you like how to use like how to implement logistic regression. So there's a lot of resources online, and pretty sure some of you have already like tried building your own model and succeeded with it. Are you able to see this empty notebook?
Yes.
Yes.
Okay. So what I want to do here is I want to show you like how we can start with a data set, like any data set. So now like we will do a classification. So Monzil shared a data set. So the data set, so it looks like this. So there's like a list of patients. I guess like, for example, for this row, so the age of this, can you see this CSV that I've opened?
Yes.
Yes.
I can see.
Okay. So yeah, there's a bunch of columns here. I think it's it's overflowing. But yeah, so I think what we are interested in this problem is like this column, this last column. So like there's 2 and 1, and we want to use this kind of information like the age, sex, chest pain type, resting blood pressure, cholesterol, blood sugar, and this kind of stuff, and try to see if we can predict whether like somebody has a heart disease using this information. So we want to use like what we've learned today and also in past lectures. So Manzil, could you clarify? Okay, so like what does 2 mean here and what does 1 mean here?
So one is, I think it's non-heart disease, and one is the heart disease.
Okay. So yeah, okay. So these are our, so I guess like these are our positives then, right?
Yes.
And these are our negatives. So we want to build out our model, like using what we have learned to see if we can find the right class for like this heart disease. So you can follow alongside me and like we can work together on this. So I don't think we have too much time to like take breaks and like watch your progress, but like let's see what we can get from here. Okay, so I'm using Google Colab. I'm sure you must have used Jupyter Notebook sometime before. So Google Colab provides free Jupyter Notebooks online, and I can run Python code here. So yeah, so the first thing that we want to do is to like upload this file and like get the data set here so we can manipulate that in Python. So yeah, so just some basic, so I want to do something like some basic stuff that will allow me to import a file in Google Colab. I learned this using Stack Overflow. And sorry. Was someone going to say something? Okay. So this will allow me to upload this txt file. And so now I'm going to import these into using pandas. So the three packages that I'm going to use, I'm going to import them. So first of all, matplotlib is an excellent Python package just to get started with visualization. And the next package I'm going to import is NumPy, right? So numeric Python, some say it NumPy. And the third package that I'm going to use is called Pandas, and it provides this feature called data frames, and which we will use extensively. So yeah, let's get started. So now we uploaded this file. I think like, so this is just like Google interface, like whatever they provide, we need to use. So we can see that the file is uploaded. Like, so this is a byte stream. So byte string. So we want to use this. We want to convert this into a pandas data frame. So I'm going to get this string, right? And I'm going to convert that into this buffer, like bytes IO buffer, just something I need to do in Google. So an equivalent in pandas would be pd.read csv, and you just put the file name, right? And this is going to read this file. And technically CSV is like, CSV means comma separated values, comma separated, right? But our data set actually like the separation is not comma, so it's actually tabs. So we need to change that character, like, so it would have been something like separator is a tab. So this is the sign for a tab. So we do the same thing, except of reading instead of reading from this file, we read from this stream. So pd.read csv from stream, and the separator is going to be a tab, right? And I'm going to call the data frame. Now let's look at our data frame. So it's the same exact data frame here. If you compare, like the first person is 70 years old, is male, I guess, or something. And there's some discrete data types. So like this is discrete, right? So there's only 0 and 1. So this is also discrete, and I don't really know what this means. But if there was a documentation, we could look up about this, and that will help us like just check whether this is even relevant for the classification problem, right? So yeah, let's just see some correlation, I guess, between these features and hard digits. Let's just plot a diagram and see something. So I just want to plot, I want to do I guess a scatter plot between age and hard digits. Okay, so this was our true thing, right? So this was a positive. This meant like the person had some kind of a heart disease, and this means this person did not have a heart disease, I guess. So looking at this, I can say that some people very young, like younger than 30, had some heart disease, and I guess about 70 had heart disease, while in the same hand, like people even older than this person did not have a heart disease. So I guess that person was an outlier. And yeah, so the first thing we want to do in our, like when we want to solve for a machine learning problem, is to see like the understand the data set, just see what we can get more. So just like this, there's a couple ways to see what we can do with this data frame. So for example, we can do a box plot. So a box plot is, it has like a lot more information. Let me make the figure a little bigger. I want, say, like 20 grids horizontally and 10 grids vertically. So a box plot has like these 5 features, like the each of these box plot has 5 features. So this is like the 25%. Sorry, I guess these are the upper and lower bounds. These are the 25th and 75th percentile, and this is the median or something like that. And we can see just from this that this serum cholesterol, so the median is about 250, right? And sex is represented using 2 numbers, 0 and 1. So it's just like here, like between 0 and 1. So we can see from that this diagram, this data set, the features in this data set, they are not normalized, right? So I want to ask, do we need normalization for logistic regression? Do we want these features to be scaled appropriately?
I think so.
Okay. So why do you think we need to normalize them?
So I think it might help during the gradient descent algorithm. That's the only one reason I think I can think of.
Okay.
If we need. But I'm not sure like whether we even need to normalize for logistic regression or not.
So yeah, so distributions, we are trying to, it's all about using we are also using the linear function, right? So the distribution of the data will be influencing, right, in the prediction. That's the thing. That's the reason why I think we need to normalize the data.
Okay. So yeah, let's normalize the data set. So we call it DF, right? So let's convert this data frame into our usual dataset structure. We call that X and Y, right? So like, what is X, right? X is like the features, right? So it's an M by N matrix. And Y is just the labels. So it's just, let's say, an M size vector. So how many rows we have? Okay, we have 270, right? So we have 270, m equal to 270. And so how many features do we have? So we have 14 columns in total. And the last column is the label that we want to predict. So the number of features is 13 here. Yeah, so we want to get X as 270 by 13 matrix and Y as just like a vector of size 270. And for this purpose, I'm going to convert this data frame into a NumPy array. I think it's like data frame dot to NumPy or something, right? And now after that, I'm going to print this. Let's look at the shape of this array, and there are 14 columns, right? And the last column was Y, the label, and the previous columns were our features that we want to use for finding Y. So X is at, we want to get all the rows, right? And we want to get all but the last one. So like something like this. So from the first column, Python is 0 indexed. So this is the first column all the way up to the last column, except the last column. And Y is just like that, but it's the last column. So if we just look at their shape now. Yeah, so it's the first 13 columns and the last column forming this vector, right? So now our task is to normalize this X. Like, so we can see the A's, right? The 6, like these have different distribution. I mean, different range. So I found that like, so there are different ways to normalize. So the one that I like to use is called the Z-score. So Z-score. So this is like assuming that like the data is actually, let's call this scaling. So this is scaling. We want to reduce the scale of each feature and make sure that they are in a similar range. And for this, I use like Z-score or like just the normal distribution. So I'm assuming that like every data is normally distributed. It's not a good approximation here because, for example, this 6, it's not a continuous variable. So we can't use, like, we can't assume that this is a normal distribution. So that's so, but still we can get some sense of like normalization in that, just like using this function, this Z-score function. This helps us limit two things, the Z-score. One, so one, it centralizes the mean. So if I use like some function called Z-score, and for this, so Z-score, and I want to pass X, and I want to like look, so this is just a Python thing. So it means to like get the Z-score independently for each column. We don't want to intertwingle any of these features. We want them to be treated independently. And so this has two properties. So what it does is it normalizes. It results the mean of each column to be 0. So that's something we want. So that like just, so like if it's 1 and 0, I want the data to be centered at like, so like this 1 is, I guess it's going to be like 0.5 or something like that. And this 0 is going to be minus 0.5. And that's going to happen for every column. But this doesn't solve the problem that like the variance of data is just different, right? So this one has like serum cholesterol, it has a long distribution, there's a lot of variation. Like the 75th percentile is about like 270, 80. And this is like 213. 215, something like that. So that's a difference of 70, while that's a lot more than the range in this feature. So I want to normalize the variance as well. So variance or standard deviation. So this z-score also sets the standard deviation to be 1 for each of these features. And conveniently, there's a package called SciPy, and you can use SciPy. It's like, I guess, so if I were to use these as my 3 base packages, I would probably use SciPy. And SciPy provides this feature for calculating, normalizing this data set. So now let's just look at the result of z-score, right? Let's put it here. Okay. So now these are just a bunch of numbers, and I want to now look at their mean. And I want to look for every column. So if I wanted to look by row, I would set this to be 1. If I want to look by column, this is 0. So first of all, I want to make sure there are 13 different means. So 1 mean for every feature, right? And that seems right. So now these values, they are very small. So 10 to the power minus 16, 10 to the power minus 18. So it's, I would say, like, this is pretty small. So it seems like the mean is properly it's set to 0. And likewise, let's just look at the standard deviation. The standard deviation for every axis. And surprisingly, this is exactly 1 for every feature. Yeah, so this is the scaling that I'm going to use now. So I want to rescale X, right? So just for the sake of clarity, the reason I did the scaling was to achieve these 2 things. So that's one. The other is the scaling. So now we have a data set and we want to predict these labels. Oh, and also I want to fix these labels. So I think the labels, they are like 1 and 2. And so 1 was positive, right, Manjul?
Yes, I think 1 was positive.
Okay. The labels really don't matter. You can have 0, 1, 1, 0, still gonna predict.
Yeah, so what I want to do is I want to convert these labels, like it doesn't matter what they are. So y is equal to 1. So that's a true, that's a like our positive case. So now what this does, like the double equals is a comparison sign. So whenever it's false, I want to treat that as 0. And whenever it's true, I want to say treat that as 1. So numpy lets us convert like these Boolean values into like integers using as type an integer. Yeah. So whenever it says 0, that means that there was not a heart disease and there was a heart disease. And now I want to update my y to be that. Yeah. So now let's revise what we have. So we have 2 things, right? X, that's the matrix that we have, and these are the labels that we want to predict. Okay. So I want to pause here and ask, so we want to build a model, we want to build a classifier. So what do we do for in the first step now? Like we have the data normalized, we have a data set. What's the first thing that we need to do?
Can we add the bias term for the X?
Sure. Okay. How do we do that? So like the bias term, okay, so that's going to add a new feature, right? So I think it's something like np.addStack, np.zeros, and I want to get 30.
So I think np.ones.
Oh, sorry, yeah, np dot ones. So I want to get like 270 zeros, and I want to horizontally stack like whatever X was there. Oh, I think there's one more bracket needed. Is it V stack? Okay, concat. Wait, how do I concat these two? And for this, so I'm just going to like use
You one more bracket go to the right.
np.concat, you need to pass list, I guess. As a list, not a parenthesis. Oh, NumPy has no attribute concat.
p dot stack and p dot concatenate. Okay, let's try concatenate. Wait. I think it's supposed to be stack actually, because we are stacking these two together. What is X? What is the size of X? So there's 206. Okay. How do we append ones to a matrix? Okay, I guess I forgot the axis. Yeah, or H stack. Let's just use. Okay. So np dot ones, I want to get M, so that's 270. And okay, let's see how this works. Let's just look at the shape first of all. Right, so one more column, and now let's verify that the first for all rows, that the first column is 1. It is indeed 1. So it has prepended the ones to our data frame. Okay. So now our shapes are like 14. So the first is the bias term and 13 features. So what is the thing that we need to do next once we have prepared our data set? So step 1, preparation complete, right? Step 2. What is step 2?
Maybe define a hypothesis.
Yes. Yes, we can define the hypothesis, but just okay. So we need to make sure that there's two kind of data sets. One that we will use to build a model.
Oh yeah.
And one we will test later on, right? So the first thing that we need to do once we have our data set is usually divide into 2 or 3 parts. So sometimes people use 2, other times people use 3. So these data sets, one is called a train, other set is called a test data set, and some people use like a validation or third data set. This is when you have a large amount of data, or when you are comparing different models, or you just want to have like a more rigorous accuracy, or more rigorous definition of your score. So yeah, but for this purpose, we are just going to use train and test. And so like we are going to use this training data set to prepare these weights, like those prepare the theta, and use it to like use those weights to get our hypothesis for this testing data set. And this will help us tell the true performance of our model. And there's a like, so the best strategy is to like go random. So don't use like the first say 80% of this for training. Like that's not an ideal solution, because usually we want to like have our train and test like both data sets coming from the same distribution. So we don't want a train like getting the first 100 rows that have only like a positive test case, positive result. We don't want that. We want them to come from the same distribution so that our training will actually work on the test. So for this is called a train test split, right? And this is, I'm not going to implement it here, but like it's pretty simple to implement using np.random.shuffle or something like that. So for this, like we can use another package called sklearn. So like sklearn has model selection, import train test split. So now train test split, this is just going to take 2 parameters. These are the required ones. And we can define, for example, a test size. And I want this to be like 20%. It depends like how much test size you want to choose, but people usually choose about like 20 to 30%. And when the data size is, so our size is actually pretty small, 270 is pretty small. But when we have like a lot of data set, we don't need this much for testing. We can use even more for training. So the more data set we have for training, the faster, the better our performance will be. And I'm going to call these as like these four variables. Okay. So we had 270 rows for our entire data set. Oh, sorry, x train.save. And for training, we got, so like for test, we got 20%, right? The test size is 20%. So this must be 80% of 270. So for the next several steps, when we build our model, we are just going to use this training data set. We won't touch the testing data set at all. Yeah, so now let's build a model. So the first thing that we want to do in our model is to write a prediction function. Like that's the most like, so I want to define the hypothesis, or actually I would call this a prediction. So a prediction is going to take a certain x, right, and a certain theta, and it's going to produce that. So we haven't defined this theta yet, but we will use it later on. And prediction, so Bimal, could you share the files that you used for your presentation?
Yeah. Just for you, right?
Yes. So I'm just going to use the formula. Sorry. I'm just going to use the formula that we were using today, and yeah, just try to build a model out of it and see what kind of, so we might encounter a few problems, one or another, and we will learn how to like fix them. For prediction, I think it was like a sigmoid function. We use a sigmoid function, and it was, so there was like a dot product between like this x and this theta, something like this. And yeah, I think that's our prediction function, but we need this sigmoid function, and let's define a sigmoid. A sigmoid takes a certain thing, a certain matrix, a number, or some kind of a NumPy structure. And yeah, I forgot what the sigmoid looked like. So I think like it's like 1 divided by
1 plus e to the power negative x.
E to the power negative x. Okay, now let's just do a quick test. So what is the sigmoid of 0?
Do you need to return?
Oh yeah. So the sigmoid of 0 should be 0.5, right? Yeah. So if we just look at this sigmoid function, okay, so this is the sigmoid, right? Okay, so sigmoid seems to be working. Now let's do just a test prediction, right? So I want to predict when the thetas are 0. So when thetas are 0, that means I'm doing a dot product with x. That should give us 0. And sigmoid of 0 is 0.5. So I guess if we predict our trained data set with just zeros, and we want 14 zeros for each of those columns, right? So this should also give us probably 0.5. Yeah. So 0.5 for each of these training rows. So it seems to be working, I guess. So now there are two more things that I need to define. So one is the cost function, right? So given some x, y, and some theta, I want to, So I want to define, given x, y, and theta, I want to find the cost function. So I guess for cost function, so there were two parts in this, I think. So one is the case when y is 0, right? So, and the other is the case when y is 1. So the cost, I'm going to call this get cost. So cost is when y is equal to, okay, let's start with 0. When y is equal to 0, cost becomes 1 minus y. So that's a 1, right? When y is equal to 0 times np.log of 1 minus hypothesis, something like this. And I need to get the hypothesis. So for this, so the prediction using x and theta, and I'm going to use that here. Is it?
I think the cost should be -2, I think.
Oh yeah, so -2 over m, right? Times something like that. So okay, so let's split this into 3 parts. So this is the cost coming from negative values. There's a cost coming from positive values. So that's, I guess, np.log hypothesis, I think. And so the total cost is just going to be negative cost plus positive cost. And this is multiplied with 2 over m or something like that. Right?
Right.
Okay. And m is just a number of features. Okay. So now let's just see if we can get a cost using our trained data set. Right? And for theta, I'm just going to pass zeros for now. So yeah, something np.zeros. I want 14 zeros for theta for this. What is the I sent X train and Y test, Y train. And I need to return this cost as well. Okay. So cost, I think, is it 2 over m or is it 1 over m for the cost function?
I think it's -1 over m.
Yeah, I think it's -1 over m as well. Is it making sense so far?
Yeah. So
Sorry, go on.
I mean, yeah, we normalize the data sets. Then yeah, I mean, this for the cost function, we select the log function. Yeah, we need to remember these things. Okay.
Yeah. Okay. So Yeah, if we just look at the slides, yeah, let's just do what we are doing here. So we define the hypothesis, we define the cost function. The cost function, yeah, so it's just going to be minus, yeah, so there's, I forgot a minus, so I think this is supposed to be minus minus negative cost. So this is supposed to be negative cost is here. So 1 minus I times log 1 minus the hypothesis, right? And for the other class, so for positive cost, just this. I think this should have been 0.69 or something, but I don't know why I got this. Anyways, let's continue. We will debug that later. So the next thing that we want to do is to get the gradient. So the gradient is the gradient of this cost, like the cost function with respect to its parameters. For that, we need two things. We need some data to get the gradient. We want to pass the theta as well for that. So the way to get gradient is it's straightforward. It's just like right here, right? So the gradient, so I want to get the difference in the middle first, and that's like hypothesis, right? So that's our prediction of x and theta minus the true values. That's our difference. And I want to multiply its like xi, so that's like a particular feature. So I guess, sorry, xj is a particular feature. And for all rows, I want to multiply these and add them together. So a quick and convenient way to do this in using like NumPy is, let me just find it. So this is something that I used to struggle a bit at times. So I just have this prepared beforehand. And for this, this is our prediction function, and m is x times theta. So I do the prediction first, right? So that's our hypothesis. Oh, I guess I need to subtract that with y, and then yeah, divide by m. Now let's just see what we get for gradient when we pass this train data set, the test, the labels for the train data set, and just zeros. Like we want 14 zeros.
So what is that x dot theta?
Oh, sorry. Yeah. So m and n are at the same. So m the number of rows, and n the number of features. Okay. So we got some gradient. So now I guess we get like everything. We have the cost function, we have the gradient. So I guess we can do this gradient descent algorithm. And for that, I'm just going to call like a train function. So now for training, we want to get this training data, right? And yeah, let's just continue from there. So I want to get these just for convenience. So I want to start with just zeros, just like 14 zeros. And we will like, so I think we can start from any number, like for theta, it's just going to converge no matter where for like logistic regression. So yeah, but I just like thought about starting from zeros, but this could have been like anything. And now let's write our loop for I in range like 100 times, I guess, right? So I want to get the cost. So cost is get cost and x, y, and theta. So I've defined this cost function above. So now I can just use it here. So the next thing I want to do is the gradient. I want to do the gradient as well, right? And the next thing after that, I guess, is to just update theta. Theta is equal to the previous theta minus alpha times gradient, right? The alpha is a learning rate, this little alpha here.
I don't think we define past alpha.
Yeah. Okay, so alpha, let's just start from 0.1 for now. We can adjust that later on. And finally, we return this theta. Whatever we trained here, we will just return this theta. And now, okay, so let's just see what we get when we train using this X train and Y train data set. Okay, so we got some values of theta, but we don't know whether these, like, how did these update? Like, are these good for me? I don't know that. So I want to look at the cost during every iteration. So I want to like build this array just for like auditing purpose. So I just want to see like how it's changing. I want to make sure that it's going down. Cost is going down every iteration, right? Then that way I know that our algorithm is learning or like at least minimizing this cost function. And we are going to return that as well. So I'm going to append this cost to this array every loop, return that, obtain it here, and we will look at the costs now. Oh, that is too many values, I think. I think we forgot something. Oh, so maybe like, okay, let's see how many costs are there. Oh, I guess like np.array. Okay, so we have 206. That is not right, right? So we just need a cost. Is there supposed to be only one cost for every row? So if this looped for 100 times, then something is not right here. So I suspect the problem is with get cost. I suspect like this is getting too many values. So now let's go back to our get cost method and let's look at the shape. Okay, yeah, this should have been just one value. And I guess we forgot the mean. Yeah, this should have been the mean actually times np mean. So if, like that's just like a NumPy problem. So that was, there's something called broadcasting in NumPy. And oh yeah, so if we just look at the value, it's just one value now. Okay, that makes sense. That's a log of 2. That's the cost when we have zeros. Okay. Yeah, so we have 100 costs. So just looking at these values, these are going down every iteration, right? So the important thing is to now just plot this and realize that it is decreasing. So it's decreasing smoothly, right? So it took 100 times. In some cases, this cost like it converges at like it goes down very fast. And then like, for example, if we loop for 1,000 times and do the same thing, yeah, you can see here that this cost decreased pretty quickly. And then after like 200, it didn't start going fast. So what can we infer from this? Can we infer anything useful from this diagram? So it's basically saying that the cost, it went, it kept on decreasing for every iteration until we like, for like, it went down for every time. But its significance, it started to like drop after 200. So for between 200 and 400 iteration, the cost did not go well a lot. The cost did not go down. So we could probably stop at 200 and get as good enough result.
So here we can say the learning become very slow.
Yeah. Yep. Yeah.
And especially it makes sense in logistic regression because the logistic, if you see the logistic regression shape at after some curve, there is a curve, right? Long curve. So because of that, the learning becomes slow.
Yeah. Okay. So we are going to use these thetas that we train, right? Like ultimately we ran this 1000 loops just to get this theta one thing. And from there we calculate like the prediction for each of these rows. And we want to make like our critical threshold to be 0.5. So whenever we get these numbers, like anything bigger than 0.5, we will treat that as a 1, just to compare. Like, so this is our prediction, right? So this is our prediction. And our true classes were, so like, I guess like, if we like use the train data set for, sorry, the test data for training. So this is y hat test, and we want to compare that with y test. So we want to compare these two. So I just want to say like, okay. So we have, okay, so there was a match, like we got like our prediction was exactly what the real values were. We have a false case. So either like we predicted the wrong class, and I can't tell whether this is a precision or recall so far, I guess. So I just want to get a few numbers before I guess we are like running low on time. So just to get some numbers. So I want to calculate the number of true positives. So that is, what is this? So this is the prediction was true, right? And the actual value was true and prediction was true. So what is false positive? So y test was false, and like y grade was true, right? Like we have these, like we have the true negative and like these. And now, so these are the 4 things that we will use, and we want to get some matrix. So one of the matrix that we can define is called precision. And I forget the formula for precision. Manzil, what was the formula for precision again?
It's true positive divided by true positive plus false positive. False
Okay.
positive, yes. True positive plus false positive.
Okay, something like this, right? And like we have the same thing for like recall and like I think like accuracy, right?
Yes.
So we have a couple metrics that we can compare. So the most important thing that we want to get is like these 4 things. With these 4, we can get the most important metric here. So this is all like, there's something called F1 score, and there's the confusion matrix. So okay, so how can we get a confusion matrix? A confusion matrix is just a summary of these 4 numbers, true positives and true negatives and like all these. So I'm just going to see if we can use sklearn for that. So I'm going to import confusion matrix from sklearn confusion matrix. And it needs the y true and the y grade, right?
It's y test and y pred.
Yep. Okay. 24, 4, 4, 22. So precision must be true positive. So I guess this is the true positive, right? So
Yeah,
what?
yeah.
Okay. True positive, is this true negative or is
Yeah,
this
the
false?
4.
I guess, okay, so it's like 24 divided by 24 plus 4, right? So, or is it like, I think it's 24 plus divided by 24 plus 22. So this is, I don't know, like, I think this is accuracy.
No,
So
24 plus 4 divided.
Yeah, so accuracy is your true positive. So 24 plus 22. 24 plus 22 divided by your all samples. So,
Okay, so that's 170.
plus 22. Yep.
Okay, so how much
No,
accuracy?
not the test samples. What is the test sample?
Okay, so test sample is just like y test
Dot.
length, right?
Yes.
No, wait,
Hold on.
this is supposed to. Okay,
Yeah.
so we got an 85% accuracy. Yay. So this is our first model, and we have an 85% accuracy. So there was a few things that I wanted to tell. So regarding this graph, this is probably the most important graph I've seen in like machine learning, the like how cost function changes over time. So this is like, so the cost was really high. It's like starts around 0.69 in logistic regression. And it goes down. The shape of this matters, like how our cost is changing over time. And this is like the lower we can decrease the cost, the better our algorithm will perform. And yeah, I guess this is like everything from the beginning, from parsing the data set to writing this algorithm for the classifier and coming up with some kind of a metric to evaluate the performance. The next step would be to maybe iterate and try to get a better accuracy like this metric and so on. And that's about it.
Wow. Thank you. I really want to say thank you, Damodar, for teaching us how to build in data science, what we call it a baseline model without using sklearn function. You showed us how we can build a machine learning algorithm and optimize it and calculate cost functions and evaluate different metrics. Thank you so much. I'd like to highly encourage everyone. So I think Damodar will post this link for the Google Colab for us in the Google Drive itself. Please feel free to go and check this out. It's a really good and important concept to learn. Uh, I would like to thank you once again to Damodar and especially Bimal sir. Thank you so much, guys. So
Thank
I
you,
think
Mo.
we're done for the class. If you have any questions, feel free to ask Damodar, Bimal, or myself, or any other concern, thoughts. Please, the forum is open now, and I'm stopping the recording.